Okay. Part 2, scientific notation. A times 10 to the n, where 1 is less than or equal to a, which is less than 10, where n has to be an integer. What does that all mean? Scientific notation, oh, that's not what I wanted to do. This is what I want to do. This means, and generally you know it when you see it, you're like, hey, 3 times 10 to the 4th power. This number, it's actually called a coefficient, has to be, and I usually say between 1 and 10. The problem with between 1 and 10 is it could actually be 1. That's what this means. This number right here could be exactly 1, or it has to be less than 10. If you get a number like 9.99999, you're okay to put that here. But if you have the number 10, then you need to be starting to change this value. Okay, so n has to be an integer. So n right here, integer means like -2, -1, -3, -4, 7, 2, 3, 6. Okay, basically negative numbers, positive numbers, but no decimals, no fractions. Okay, so that's kind of what it is. You worked with it before, but let's talk about some things here. Well, if I were to move my decimal, right now it's right here, I'm going to move it 1, 2, 3, 4 places. Why am I moving it 4 places? Because that coefficient, that lead number, needs to be between 1 and 10. If I only move it this many places, oh, I'm trying to cover it up with my hand, that's not going to work, then I have 42. If I move it over here, then I have 0.42. But if I move my decimal here, I have 4.2. Okay, 10 to the what power? Well, how many places did I move this decimal? 1, 2, 3, 4 places. So I have 10 to the 4. Okay, this number here, 5.762. Notice how I give all the digits after this until they start hitting the zeros. Okay, so 5.762 is between 1 and 10. 1 could be this number, but it's obviously not. And then times 10 to the what power? Well, let's count. Or as my child says, count with me. 1, 2, 3, 4, 5, 6, 7, 8, 9. So it's 10 to the 9th power. Why did I move it there again? So that I would have 5 points. So that number would be between 1 and 10. All right, here I'm going to move the decimal this way. All right, so I know I'm going to have 7 times 10 to the what power? Let's count. 1, 2, 3, 4, 5, 6, 7. Well, that's kind of weird that it went to the 7th power. Oh, wait a minute, not 7th power, it's the -7th power. Okay, it's got 6 zeros, but I've got this other decimal spot right here, so that's why it's going to be to the -7th power. If you think about just this part alone, 10 to the 9th is like 1 with 9 zeros after it. Okay, and that means I take 5.762 times 1 with 9 zeros behind it. If I take 7 times 10 to the -7th, that's like saying I have 0.000001. All right, and then I take that times 7. So if I do this here, I want to move the decimal to this spot right here, because then I have 1.23 times 10 to the what power? 1, 2, 3, 4. And it's the -4th power. Why am I doing that? Because I move the decimal to the right. This is weird. I'm moving the decimal to the right, so I'm giving it a negative exponent. Moving the decimal to the left gives it a positive exponent. Okay, let's go the other way. I converted here from customary or typical standard notation into scientific notation. Here I've got scientific notation, and now it's going to make more sense. I'm going to move the decimal 3 places. 1, 2, 3, and now it's to the right. 5, 1, 2, 3, meaning the decimal place is moved that way. Now I'm going to move the decimal places 5, 3, 4, 5. I have to fill in these with zeros. So I have 3, 1, 2, 9, 0, 0. The decimal was here and I moved it 5 places. 1, 2, 3, 4, 5. Put my commas in, especially with big numbers like this. 1.2 times 10 to the -3rd means I move this decimal back 3 places. 1, 2, 3. And I have to fill in with zeros. Well, this is already accounted for 1 spot, 2, 3. So the number ends up being 0.0012. And this is 4 times 10 to the negative 7th. So I'm going to have a 4, and I'm going to move it back 7 places. Well, this will be 1, 2, 3, 4, 5, 6, 7. Put a dot. No commas in those when you have decimals. All right, moving along. All right, we need to evaluate, express the answer in scientific notation. I know it is so easy to go to our calculators, and I actually thought about just let me do the calculator stuff. But here's the deal. I think you just need to see this once before you go off to college or whatever you're going to do. Even in your science classes, this may come in handy. Those are kind of called the coefficients. You have 8 and you have 2. We'll multiply them. You get 16. All right, and then I have times 10 to the, oh my goodness, I have a 9 here and a 7, and this is the whole point of this lesson because we just built off of when you're multiplying with like bases, you add your exponents. Okay, now you're like, Mrs. Talley, that can't be right. Maybe I'm going to get extra credit because I'm going to be the first to say to you, hey, you made a mistake. This number has to be between 1 and 10. Ooh, 16 isn't between 1 and 10. So what I'm going to do is I'm going to rewrite just this number, okay? I'm going to rewrite this number. It's going to be 1.6 times 10 to the first power. All right, but wait a minute. I still have 10 to the 16th power. So now I really have 1.6 times 10 to the 17th power. That's your answer. And I know you could have put that in your calculator and had it do for you, but it's kind of nice to know that you could do this manipulation without having to use your calculator. All right, and then as I say that, look at this next problem. 3.1 times 7.9. Let me see if I have my calculator. Oh yeah, but it's kind of cool just to know you can take your coefficients times each other. 3.1 times 7.9 is a 24.49. Okay, when I'm multiplying with like bases, here we got like bases, I'm going to add these exponents, I get negative 3. Okay, I can switch this right now, or I think in this case, I'm going to move the decimal right away. Negative 3, so I'm going to go, oh, I don't like that either. I am going to switch it just to make our lives better. I don't know, I'll do it the same way I did the other. I'm going to go 2.449 times 10 to the negative first. Okay, so 24.49 is the same as 2.449 times 10 to the negative first. Oh no, it's not. I need to take it to the first. See how I checked that on my calculator? How hilarious is that? Okay, so 2.449 times 10 gives me the 24.49. Okay, so this is equivalent to this. And now I have to take it times 10 to the negative third. Well, now I'm going to combine these terms together. So I have 2.449 times 10 to the negative second. When I'm adding exponents, that's what I'm going to get. And that's scientific notation. All right, over here. 8 divided by 4. That's crazy. You can do that. Take this little piece and divide it. You can. You get 2. And when I'm dividing with like bases, guess what I do? I subtract my exponents. So I have 4 minus 2 is 2. And there it is, scientific notation. Okay, let's do it one more time. This is a little bit more with the book ones. And once again, I think if you have something like this, you'll probably use your calculator. And we're going to start off with just doing kind of the same process. Okay, so 2.38 times 7.56 is 17.9928 times 10, and then once again I look at this, and this I'm multiplying with like bases, so I add my exponents. So I have 10 to the 8th power over 4.2 times 10 to the 18th power. Oops, this has to be 18. All right, I'm just going to calculate this on my calculator. 17.9928 divided by 4.2 gives me 4.284 times 10. 8 minus 18, because when I'm dividing with like bases, I subtract my exponents, so that's the negative 10th power. All right, and that is scientific notation. We're going to leave it like that. And once again, I just like to show that to you. I know that 99.9% of my students will go off into the next math class or college or whatever, and you're just going to plug that in. But I think it's good to see, especially if you have something like this on ACT, MCA, some other kind of test. Hey, I could just take those first two and multiply. Or I don't know, if you're on some game show where you can win $1 million. All right, example 13. There are about 5 times 10 to the 6th red blood cells in 1 millimeter of blood. All right, that's how many red blood cells in one thing of blood. A certain blood sample contains 8.32 times 10 to the 6th red blood cells. So this is like somebody's counting the red blood cells on their computer, microscopic computery thing. About how many millimeters of blood are in the sample? So we're going to say how many of these go into here, or this 8.32 times 10 to the 6th divided by 5 times 10 to the 6th. Same process. I'm going to keep showing you 8.32, and I'm going to divide that by 5. That gives me 1.664 times 10 to the what power? 6 minus 6 is 0. What's anything to the 0 power? And notice I'm only doing this part here. 1. So I actually have, you don't need to write this out, times 1. But now you do need to write down the answer. It's just 1.664. And what should I say? How many millimeters of blood are in the sample? So this must be millimeters of blood. Oh, milliliters. Silly me. Milliliters. All right. Example 14. A petri dish started with 3.6 times 10 to the 5th germs in it. A half an hour later, there are 7.2 times 10 to the 7th germs. How many times as great is the amount a half hour later? So this times what gives me this, or this number divided by 3.6 times 10 to the 5th. Okay, I'm saying how many of these go in there? How much bigger is this than this? Okay, 7.2 divided by 3.6 is plain old 2. When you're dividing with like bases, subtract your exponents, and that is scientific notation. So it's 2 times 10 to the 2nd times greater, otherwise known as 200, because this is 100, and we're taking it times 2. All right, so it's 200 times greater is what they're basically saying. And that is it.